we're going to start from the perspective that we've already gotten our mass to space, be it the space elevator or rockets. We've already gotten to space. And so we're focusing on actually the travel, constructing our craft and moving us to interstellar space to our target at Alpha Centauri. So hopefully this works. All right, so that's me. So this is a chart from a 100-year starship to demonstrate the scale of our travel to another star. So let's say we're starting in Los Angeles to New York City, but we're going to replace Los Angeles with Earth and Alpha Centauri with New York City. We know that that's about 4 light years away, 25 trillion miles. And if we look at our Voyager spacecraft, we see that on average, it's only gone about 1 mile in this journey. So we've got a long ways to go. But the focus here is not just on the journey, but what do we need to get there, particularly for a crewed mission. You saw this from Dr. Jemison's slides, that this is going to take a different type of thinking and different types of technology and looking at different capabilities, radical leaps in our thinking for this. But it is a realizable goal. And what you've heard today from the speaker in the morning and this afternoon is that we do have technology demonstrations that can get us there. And actually, if we can reduce the time to travel, the crewed mission becomes more viable. So let's take a look at some of the possibilities for that. But first, let's look at how we travel now. All right, we all got here, and we had a vehicle that we provided some energy to for propulsion. Either it was gas, electric charge, or aviation, what have you. We had to navigate. We had to have some room for navigation. We wanted to do that safely. We wanted to arrive safely and sustainably if possible. And we wanted to communicate with others. We worked remotely. We plugged into the USB on a plane or a car. And we wanted to take selfies. I want to tell my friends that I'm here at Breakthrough, and I'm going to send those selfies to my friends. But all of those things that we do when we travel require energy. And it will be the same for our interstellar travel. So the scales and types of energy that we have to manage, obviously propulsion, we have to keep our craft moving forward, power generation, our energy storage, all of these here, crew comfort is going to be important as well as life cycle management. So I'm going to separate the propulsion from everything else and lump these into subsystems. You've heard about the propulsion options, so I won't go into those into detail, but just for some perspective. From 100-year starship, we said that we need 1,000 times the speed of Voyager to arrive in 70 years, a human lifetime. The Breakthrough Starshot that you heard this morning, traveling at about 20% the speed of light, could get us there if we can scale this up to in 30 years. And you'll hear more about that from Phil Lubin this afternoon. So let's talk about some of the scale-up propulsion possibilities. All right, this is, again, if we can scale these up and have them work for the light sail, it's a very simple design. It is only limited by the laser, the size of the power source, 29 years. Now, fusion and fission are similar nuclear, but obviously fusion, you're putting the bonds together to make the plasma. Fission, you're splitting them apart. But the whole idea is to take this hot plasma, push it out the back to propel you forward. The fission is a two-step process, so that one's going to take a little bit longer. If we can scale up the fusion, 36 years. And just for giggles, the antimatter, for that one, the creation and the storage of the proton propellant is going to be a challenge, relativistic effects, but if that works, if it could work within 5 years. But these are the more realizable for this discussion. So for the subsystems, there's a paper from the ISC by Mason Peck and some the others from Breakthrough Starshot that estimated that the subsystems were about 10% of the total spacecraft mass. And so we're working with that as an assumption for the full spacecraft as well. But the challenges go well beyond just that. We can't just scale up our systems and plug them in. We also need communications and navigation, not only internal communications, but also the ones that I said before for our selfies. We want to talk about onboard computations and energy storage. So let's take a look at some of the subsystems. So for power generation, at least for part of the trip, the photovoltaics may be an option. All of these, so if we're moving from this solar system out to Interstellar, we can use photovoltaics for part of the trip. Fission and fusion, I talked about before, also can be used for power generation, and the RTGs, the radioisotope thermoelectric generators that are used on Voyager right now, and others, those can also be used for power generation. But we also have to not only generate power, we're going to have to store it as well. And so for energy storage, our regular lithium-ion rechargeable batteries are probably not going to be the greatest source for us for this type of trip. So the solid-state batteries are a very good option because they replace the liquid electrolyte with a solid electrolyte. And so you reduce the problems that you have for thermal runaway and overheating with this. For example, Toyota has just talked about a demonstration battery that they have right now that goes 900 miles on one charge. All right, and that's like almost double what you can get with a regular lithium-ion battery pack. Fission as well is also an option for energy storage, as well as our nuclear batteries. And the nuclear batteries are described in the paper by Mason Peck et al. So one of the other things we have to talk about is the energy that's required for crew health and wellness. The idea that we hear about make it, don't take it from the Artemis and Mars missions, we have to do as well. There's a lot of work being done in additive manufacturing for space applications. All of that's going to require power. Onboard communications, again, power. The work and science experiments, we have to provide power for those throughout the mission. And entertainment and play. What types of entertainment and exercise? You can't just plug in your Peloton that's going to take 2.5 kilowatts of energy and just take that up there. We have to think about those in different ways. And also the old equipment that was used in previous missions may not play out very well for this long of a flight. Personal and mental health care. We still have to have medical devices. We have to think about what does mental health care look like for this type of trip. And artificial gravity. So we know that as humans, we don't do very well in a long period of time without gravity, and we don't know how that will affect us on this long of a trip. But again, one of the things that's being worked is zero gravity. I was very pleased to see on the front of my American Society of Mechanical Engineers magazine, the orbital assembly for the zero gravity, no problem. So my point is that a lot of these technologies that we need and we will need are in nascent form and can be scaled up or used or repurposed for this type of trip. So the power required for our crewed interstellar travel, it's achievable. Pieces of it are being worked right now, but we need to pull those together for this mission. The supporting technologies are there. They just need to be either scaled or studied for this type of trip. And the power requirements can be addressed to facilitate a successful mission safely and, more importantly, sustainably. And with that, I will say thank you, and I'll take any questions at the break.